Taylor's formula for a function of two variables. Let f, this f be a function of two variables x and y. F is a function of two variables x and y. F of a plus h b plus k. F of a plus h b plus k is equal to f of a comma b plus h times del by del x plus k times del by del y f of xy calculated at the point a comma b plus 1 by 2 factorial in bracket h del by del x plus k del by del y square f x comma y calculated at AB plus and so on plus 1 by n factorial h del by del x plus k del by del y to the power n f xy calculated at AB plus the remainder r. So now earlier we have discussed Taylor's formula for a function of one variable. One variable we discussed now. We are discussing the Taylor's formula for a function of two variables. Here f is a function of two variables x and y. So if I want to expand this function f about the point a and b, about the point a b, this is the formula where the remainder Rn is given by Rn equal to 1 by n plus 1 factorial h del by del x plus k del by del y to the power n plus 1 operating on f x y and then calculated at the point a plus theta h comma b plus theta k where theta lies between 0 and 1. So Taylor's formula for a function of two variables is this is first order partial derivative operating on f calculated at the point a and b. This is second order partial derivatives operating on f and then calculated at the point ab, and so on till nth order partial derivative operating on f calculated at the point ab plus the remainder term, where the remainder term is given by this expression. This is the Taylor's formula for a function of two variables. Taylor's formula for a function of two variables. Formula is we can calculate the extreme values of a function. As you know, the maxima and the minima. The maxima and the minima of a function is okay, so this is fine. Now using this Taylor's formula, function amagi maxima and minima. Function of a one variable for a function of one variable. So for example, for a function of one variable f of x, the local maxima or the local minima say koi thi hai kadi first at the point, suppose the point x equal to a. The function has an extremum value. Let us suppose that at the point x equal to a, the function has an extremum value. What are the necessary conditions? The necessary condition that the function f of x has an extremum value at the point xa is that the necessary condition is that the first order derivative of f calculated at the point a should be equal to 0. Aduna high function z f of x high function z mazi x equal to a high magi extremum value it can be either maximum or minimum. Extremum value the first order derivative of the function calculated at the point a should be 0. This was a necessary condition. Taylor's formula sizinarga equina makhatana kari proof to vi ibd is a necessary condition aduga if the second order derivative calculated at the point a is less than 0, then this point x equal to a is a local maximum. The function f of x has a local maximum value at x equal to a if the second order derivative is less than 0 and the first order derivative at the point is 0. This corresponds to local maxima. Number 1. Number 2, the first order derivative na 0 chalava, second order derivative na greater than 0 tardi, this corresponds to a local minimum. Local minimum of f of x. The function f of x has a local minimum value at x equal to a if the first order derivative at a is 0 and the second order derivative at a is greater than 0. Second order derivative local maximum and local minimum. What happens if the second order derivative is 0? Then you take higher order derivatives. Higher order derivatives logani ko aduga check togani. So second order derivative is 0 we should take higher order derivatives. With third order derivative check tarani, third order derivative to 0 taragadi, fourth order derivative check tarani, fourth order derivative to less than 0 already local maxima, fourth order derivative to greater than 0 already local minima, and so on. Sigi ideas we can extend this idea to a function of two variables. Function of two variables ta equina sigi local maximum and local minimum value say sigi idea say we extend the way for a function of two variables. Suppose my function f is a function of two variables. It depends upon two variables x and y. F and this function f of x and y function z magi local extremum value f of x and y has a local extremum value, local extremum value at a comma b. F of x and y has a function of two variables has a local extremum value at the point a comma b. See, we should have a necessary condition. Necessary condition. What is the necessary condition? For function of one variable, the necessary condition was that the first order derivative at the point a was 0. For second order derivative, for function of two variables, the necessary condition that this function has a local maximum value at a comma b is that the partial derivative with respect to x calculated at the point a comma b should be 0, and also the partial derivative with respect to y calculated at the point a comma b should also be 0. Aduna a b hariba point da f xy hariba function ji extremum value lege harigadi by necessary condition kari satisfy the partial derivative with respect to x at the point ab should be 0, and the partial derivative at the point at the point ab, the partial derivative with respect to y at the point ab should also be 0. These two conditions are necessary conditions, but they are not sufficient conditions. Sigi condition anije necessary condition ni habi kai no sigi extremum value legi haragadi sigi ani 0 tagadabani haba tadabya de. So sigi ani 0 tare haiduna ai function sigi he the extremum value he ta legi habi legi chumbra aduni chumde ko aduna kai hai sigi these two conditions are necessary conditions, but they are not sufficient conditions. To check that, let us consider an example. Hello. I'll repeat it. F of x and y, this is a function of two variables. Sigi function jigi a b hariba points the local extremum value amal lay haiba tarakadi necessary conditions se kaino partial derivative with respect to x at the point a b should be 0, partial derivative at the point ab with partial derivative with respect to y at the point ab should be 0. Partial derivative ani is 0 tagadabneba ani is tadragadi extreme value label yaroeba necessary condition neba. Sigi condition ani is sufficient or bra. Sigi condition ani is satisfied or function sigi extremum value heta layrani haibra haigadi no sufficiently oide. I can consider examples where these two are 0, but the function does not have an extremum value at that point. Other example I might discuss. So let us consider the function f of x comma y. This is equal to x square minus y square. So this is the function. Sigi function so example So what is the partial derivative with respect to x of this given function? The partial derivative with respect to x is equal to twice x. And what is the partial derivative with respect to y? The partial derivative with respect to y is minus twice y. So now partial derivative see 0 sale. This becomes 0 when x equal to 0. This becomes 0 when y becomes 0. So these two partial derivatives, they vanished. They vanish at the point. Origin. They vanish at the point. They vanish at a equal to 0, b equal to 0. They vanish at the origin. You consider this as a function of only x. Y is fixed or y value is fixed or when you consider this as a function of only x. Say for example, y is fixed or y equal to 0. You put y equal to 0. Now this function becomes a function of only x. So if I put y equal to 0, then f of x becomes x square. That regards my f of x. I have the f of x f of x y 0. This is equal to x square. This is a function of only x. We have kept y fixed at 0. Now look at this function f of x0 equal to x square. This function magi maximum value this function can go up to infinity. Magi maximum value but it has a minimum value. This function cannot be negative. Magi minimum value 0. When x equal to 0, this becomes 0. Otherwise, it is always a positive number. So this function has a minimum value when x equal to 0. So this function has minimum at the point 0, 0. When x equal to 0, y equal to 0, this function has a minimum. So if I consider this as a function of only x, it has a minimum at the origin. Now, let us consider this function as a function of only y. So second case, if x equal to 0, wherever y function this becomes minus 2y. Sorry, minus y square. This becomes minus y square. When you put x equal to 0, this becomes minus y square. So when I consider this as a function of only y, keeping x equal to 0, the function becomes minus y square. So x is 0, so already this becomes minus y square. And the function minus y square has a maximum at 0, 0. Has a maximum at 0, 0. So this function, if you consider y, if you take y equal to 0, and then it becomes a function of only x, and it has a minimum value at 0, 0. This function, if you consider when x equal to 0, it becomes a function of only y, and it has a maximum at 0, 0. So, when we move along the x-axis, the value of the function has a minimum value at 0, 0. When we move along the y-axis, the value of the function has a maximum value at the origin. Thus, this surface has a maximum in the yz plane and a minimum in the xz plane at the origin. X direction origin the minimum y direction origin the maximum function 0, 0 origin local maximum local minimum local maximum local minimum direction, in any direction you move, it should always be either a minimum or a maximum. Maximum or minimum local maxima when you move along any direction, maximum local maxima point maximum city x direction origin the minimum y direction origin the maximum this point is neither a local maxima nor a local minima. This point is called a saddle point. Saddle point. It's a double D L E saddle point. Saddle point forever. So f of xy has a local maximum value at a and b necessary conditions. The partial derivative with respect to x at the point should be 0. The partial derivative with respect to y at the point should be 0. Point AB critical point. This AB point AB is called critical point. Critical point. Partial derivative 0 chapada. Partial derivative 0 chapa point to critical point. Critical point function maximum minimum critical point function neither maxima nor minima oibasu yai haibine ko aduna point amase function sigi critical point oige haragadi sigi point se function sigi critical point oige haidi kaido godabno partial derivative with respect to x 0 chagadabni partial derivative with respect to y 0 chagadabni ado sigi condition ani jina sufficient oirabra haidi oide sigi condition ani ji satisfied tawjaraga su hariba critical point sida ai function ji maximum oidabusu yai minima oidabusu anima oidabu yai example di in this particular example we have seen that when we move along the x-axis the critical point which is the origin at this point the function has a minimum but when we move along the y-axis at the critical point the function has a maximum aduna in a different direction matamda amugna minimum oire amugna maximum oire aduna habdi kaino maji local maxima ju oidre local minima ju oidre sigumbu point sigo koni kai kawi saddle point kawi this is called a saddle point sigi let me just share with you one example saddle point sigi ka so sigi ji sigi function sigi ka sigi function x square minus y square equal to z harijine ka equal to z harisi and let us plot this function sigi function ji plot tor yenga se ba so let me share screen this is a plot of the function x square x square minus y square equal to z natraga x square minus y square minus z equal to 0 this is a plot of the function when we move along the x-axis along the x direction this function has a sigi function z this function of x and y it is a surface surface ni aduna so this is along the x direction when we move along the x direction the function has a minimum when we move along this x direction the function has a minimum this is the x-axis this is the x-axis so when we move along the x direction the function has a minimum at the origin right so when you move along the x direction the function has a minimum at the origin and this is the y direction so this is the y direction now let us look at the y direction so when we move along the y direction this function has a maximum at the origin this is the origin so when we move along the y direction the function y direction now this is the y direction when we move along the y direction the function has a maximum at this point which is the origin and when we move along the x direction this is the x direction the function has a minimum at this point so this is like a saddle sagol thawbasina sagolgi naganda thaba sagolgi sabaldo this is like a saddle this looks like a saddle horse saddle so this point where this critical point along where the function is minimum when we move along the x-axis and the function has a maximum when we move along the y-axis such point is called a saddle point so this is the plot of the function and this is the point this is the saddle point let me stop sharing okay adu origadi koi next the maxima and the minima do the line amatan yoba yai let me bring it here oh hello let us consider a function of two variables let us consider a function of two variables. The function f of x and y has a local maximum value at the point a, b if f of a plus h, b plus k is less than f a b for all h and k. A b high points the function in the maximum at all other nearby points. This is all other nearby points. Function की value a b function की value AB high points the function local maxima like the value of the function at the point AB should be larger than the value of the function at all nearby points.
Sindiko koi local maxima ki definition ja. The function f of x and y has a local maximum value at the point AB if f of a plus h b plus k is less than f of ab for all h and k such that modulus h is less than delta and modulus k is less than delta, where delta is some sufficiently small positive number. So meaning the ab higher point the function local maximum value like the value of the function at ab should be greater than the value of the function at all nearby points. The function has a local minimum value at AB if the value of the function is less than the value of the value of the function at the point AB is less than the value of the function at all nearby points. So these definitions have the following geometrical interpretations. The equation z equal to fxy describes a surface in three-dimensional space. If fxy has a local maximum value at AB, and if we denote this maximum value by C, then the plane z equal to C equal to FAB is a tangent plane to the surface at the point x equal to A, y equal to B, z equal to C. And all points on the surface z in the neighborhood of this point lie below the plane. Maximum points tangent all values of the function lie below the tangent except at the critical point. Idea is ini. Idea is like okay. Necessary condition critical point or my necessary condition the derivative of f with respect to x should be 0, the derivative of f with respect to y should be 0 at a and b. Saddle point example I'm discuss so along this direction it is a minima, whereas along this direction it is a maxima.